Hi everyone. In this chapter, we are going to study about approximate analysis method of indeterminate structures. Why do we need approximate analysis method is that so far we have studied about statically determinate structures where force equilibrium equations are enough to find the unknown support reactions. If you have three unknowns, we can apply the force equilibrium equations, which are sigma f sub x must be 0, sigma f sub y must be 0, sigma moment about any point of the structure or free body is 0. So we have three equations, so that if you have three unknowns, it's enough to solve for three unknowns. But if it's more than three, then we need one more or two more equations. We call those structures as indeterminate structures. So to come up with the additional equations for the additional unknown, we are going to use sophisticated exact method or approximate method. And in this approximate analysis method, we are going to utilize inflection point. When you draw bending moment diagram, you are going to see at some point the sign of my bending moment switch from positive to negative or negative to positive, so that where your bending moment is 0, then you are going to have inflection point. So that from experience, engineers have found that the inflection point is behave very similar to real hinge, and we can find out where the inflection points are from our experience. So utilizing that approximate location of inflection point in your structures, in common structures, the analysis result was very, very exact, practically acceptable range. So in this chapter, we are going to study about indeterminate structures and also portal frame with truss attached, and frame with gravity loads, and frame with lateral loads. In frame with lateral loads, we are going to use portal method and cantilever. Okay, now let's study about indeterminate trusses first. Always truss is simpler than frames. So if you look at textbook, they always cover truss first and then frames. Because in truss, the member forces are in either tension or compression. There is no moment and no shear force. So it's simpler. Let's consider this indeterminate structure first. How do I know this truss is indeterminate structure? Of course, you can use the determination equation, but simply when you have this crossover, if two members are crossing without node at that location, then the entire truss is already indeterminate truss. Anyway, okay, we have indeterminate truss here, and how can we find the member forces? It's a very difficult story, but in this chapter, we are going to assume approximate relationship between member forces. So we will find it very, very easily. Okay, take a look at it. All right, and of course, to analyze any truss, whether it is determinate truss or indeterminate truss, we are going to get the reaction first. And then we are going to cut wherever you need to calculate the member forces. For example, we want to know this member force, and this and this. Then we need to cut it there like this. So wherever you cut your member, there is member forces. Okay. So in approximate analysis, we are going to have two cases where your members are very slender. Here, slender means it does not have resistance to compression force because it will buckle. And second case, non-slender, that means your member can resist both tension or compression. Okay, let's take a look at this free body diagram. And no matter what, your sigma f sub y, in this case vertical direction, must be 0. F1 definitely does not have vertical component. F2 neither. Fa has some vertical component, and Fb has some vertical component too. So vertical component of Fa and vertical component Fv must be same as R1 reaction at A. Okay, if you write it down in mathematical form, we are going to have this. But still, we do not know what is Fa, what is Fb. We do not know. We know what is the reaction by now, but we cannot solve it. So that we are going to assume some relationship between Fa and Fb in approximate analysis. All right. In this example, we are going to determine the member forces in the members. Again, I know the member forces will be in either tension or compression. No bending moment, no shear force. And we are going to make a cut there, wherever you need to calculate your member force. And we have member crossing here, so that we know this truss is statically indeterminate structure. Okay, let's make a cut here. Of course, make sure that you already got your reactions. Otherwise, your free body diagram is not in equilibrium, and all the subsequent calculation will be wrong. So please make sure your free body or entire structure are in equilibrium. Okay, we made a cut, imaginary cut here. Okay, we made a cut here. 1, 2, 3, 4. 1, 2, 3, 4 unknown member forces are there. Again, once again, by now you calculated your reaction. Now this is unknown. So that we have 1, 2, 3, 4 unknown. But we have only 3 force equilibrium equations. So we need one more equation. In this chapter, please pay attention to where you're going to get the additional equation. Okay, that is, we know vertical component of F3 plus vertical component F4 is 10K, so that it will be in vertical equilibrium. Okay, again, y component of F3 plus y component F4 will be 10. That is additional equation. Okay, so that you need to focus on where you need to pay attention. Okay. In this chapter, how you get the additional equation. Okay, again, this equation is approximate relationship. from our structural analysis experience. Okay, and the y component is sine, so that 3 over 5 is sine, whatever angle here. So you've got this equation. So that F3 and F4 are both 8.33 because these diagonals are non-slender. So they are capable of carrying compressive and tension force. So that, how do I know F3 is the same as F4? They may not be. They may not be. We assume so based on our experience. Even though they are not exactly the same in practice, they are very close, very close. So that we are going to assume F3 and F4 are the same. That is approximate relationship. So then my answer is 8.33. Once you've got 833 here, 8.33, then if you analyze joint A, then only one is unknown. Okay, next example is a truss with slender diagonals. Any slender members in structure will not be able to carry compressive forces because it'll buckle. So that when you have X bracing, if one is in compression, the other one is in tension. So either one will work because if the slender member is in compression, it will buckle and it will not carry any resistance. So in this case, this is compression member and this is tension member. So the compression member will not be effective. You may think it as zero force member or simply neglect it. Okay, with that, let's start. We are going to make imaginary cut and you are going to get corresponding free body diagram. So that in this case, you are going to have 1, 2, 3, 4 unknowns. And I know FAE is in compression, so it will be assumed to be 0. In that case, vertical component of FFB must be 10K. Like this. So this is again approximate analysis, but it's very close to the reality. So FAV is found to be 1657. After found FAE is 0, then you can find FAB. Okay, as a repetition, let's solve example 7.2. We have the truss shown, and as you see here, diagonals are slender, so that either X bracing will work, not both of them. Okay, let's start. Let's say we need to find out member force here and there. and here and there. So we need to make a cut in here. Like this to get two free body diagrams. Of course, I'm going to take left hand side because the left hand side free body diagram is a lot simpler than a right hand side. So that this is my free body diagram. Okay, so that wherever you cut the member, there will be member forces, internal forces. These four internal forces are in equilibrium with this 1, 2, 3 external forces. Four unknowns, so that we need one more additional equation. Instead of rigorous analysis, we are going to come up with approximate equation. Okay, which is F4 is 0. Simply neglect F4. Then you are going to have F1, F3, and F2. So F4 is not there, it's already 0. That is approximate relationship. Very convenient and very close to the reality, but not exact. So F3 will have only, I'm sorry, once again, F3 will have Y component, and that will be AK minus 2A and 2K and minus 3K. So F3 is 2. So after found the F3 as 2.83, then F1, F2 can be calculated easily. So F2, F1 remaining. Okay, but you can easily solve for it using three force equilibrium equations. Okay, we have now polar frames. When you have a frame without expressing, we call it polar frame, so that it can be used as entrance of huge truck or something. So these days, internet industry use the term portal as an entrance. Anyway, when you have portal frame, we have pin supported or fixed end. Of course, when you have pin supported, we are going to have two unknown reactions at each support location. So again, we have three equilibrium equations. So in this case, we need one assumption or one approximation required. Okay, and if it's a fixed supported, then each support will have three unknown reactions. In this case, we are going to need three assumptions. When you have a portal frame with pin support, we are going to have two unknown at each support. But you still can get your VB and VA by considering some of the moment about A must be 0. Okay, and now if you are considering your moment about A here, then you can clearly see this is a seesaw game between P and VB, so that you have this much of moment lever for P and this much of moment lever for VB. So they must be rotationally equilibrium, so that you can get VB value pH over L. If your VB is pH over L, considering sigma f sub x, sigma f sub y must be 0, and VA must be the same as VB in magnitude and opposite in direction. Now, we still have HA, HV unknown, while we used already two equilibrium equations, which is a moment about A must be 0, sigma f sub y must be 0. So we have only one equilibrium equation left, but we still have two unknowns, so we need one more equation, which is we are going to put inflection point at midspan of beam. The reason being, when this portal frame deflects under the action of P, the deformed shape of your beam will be like this, double curvature. So that inflection point must be somewhere around in the midpoint. It's not exactly at midspan, but we are going to consider it's close to it. And that is a correct assumption and pretty exact assumption. In that way, we can put a real pin in there and we can analyze the half of the structure. So if you take left half of your frame as your free body, you are going to have 1, 2, 3 unknowns. First, you are going to consider sigma f sub y must be 0. Then you can find this vertical force must be same as your vertical reaction at A in magnitude, and direction must be in opposite direction. And next equilibrium equation is sigma m sigma moment about A must be 0. Okay, we are talking about sigma moment about A, so that P times H clockwise, HC times H counterclockwise, PH over L times L over 2 counterclockwise. So that in that way, we can calculate HC as P over 2. If this force is P over 2, then HA must be P over 2, because we have P to the right and half of P to the left, another half of P over 2 to the left. And for the remaining half, we are going to have action and reaction. So this must be PH over L, but going down. And this force to the right, P over 2. And then this one must be P over 2. So that in this page, what you have to learn is, if you apply P to the lateral direction of a portal frame, the base shear or horizontal reaction at support is P over 2 and P over 2. This is again is approximation, but very close to the reality. But you need to memorize these two values. Okay, when you apply P, each column will take care of P, 50% of P. So the horizontal reactions of each columns are equal, and which will be half of the applied lateral force. Okay, if your portal frame has a fixed support, then each support will have 3 unknowns. Because we have 3 equilibrium equations, we need 3 assumptions, 3 equations, 3 approximations. This is 3. We are going to assume inflection point at midspan of beam and mid-height of each column. Then 1, 2, 3 condition. What are those conditions? Bending moment at these 3 locations is 0. The reason because If it's fixed support, then deflected shape of column is going this double curvature beam as we discussed, and this column is same deflected shape as the left column, so that approximately at mid-height of column we are going to have inflection point, and the location is very close to exact solution. Okay, and memorize the location of inflection point, even though that is approximate, but very close to the practical case. So similarly, what we have done in the previous page, you can get all the forces. But again, you need to memorize. You are going to start your analysis with vertical reaction first and then horizontal. Horizontal reaction is just P over 2, half of your lateral force. Okay? Instead of going through unnecessarily wasting time in the quiz or exam, you just go P over 2, P over 2, as long as you are asked about approximate analysis of frame. Okay, now if we have a portal frame with a partial fixity, and you may wonder what is a partial fixity. If it's not fixed support, then what is a partial fixity? Actually, this matter is not clearly understood by some novice engineers. So that this is, I think, a good opportunity to find out what is a rigid connection and what is a fixed support. If this column is rigidly connected to this foundation, then the angle rotation of the column will be angular rotation of the foundation will be the same. But if the foundation is not good enough, or not big enough, or not heavy enough, when column try to rotate, entire foundation may rotate, so that relative angle change between column and foundation is zero, which is rigid connection. But if it's not fixed support because rotation occurs. So in this detail, it's a rigid connection between column and foundation, but foundation is not good enough to provide fixed support condition. Okay, in this case, we are going to have three inflection point total, one in the midspan of beam and 1/3 height of column. So that total 3 and one in the beam and one in each columns. Okay, memorize it. Now frame with a truss. At times, combination of frame and truss are used for economical purposes. In that case, most important thing, in addition to the content of the textbook, is that you need to be able to see the entire truss as a rigid body. Okay, again, that means at first, angle between column and truss was 90 degrees. Then, after application of the lateral force, still the 90 degree will be maintained, rigid, okay, with connection. In this case, we are going to apply the same assumption as those used for simple portal frames, which is half height of column. We are going to have inflection point, which is hinge. Of course, the column shear at base location will be half of the lateral force. P is applied, then because we have two columns, P over 2 and P over 2. Again, this value also is approximate value, and location of the hinge or inflection point is also approximate location, but pretty good assumption. Okay, let's solve an example. We are going to determine the external and internal forces acting on the frame. First, we are going to assume inflection point, half height of the column. Please note that your column length is right underneath the rigid body, so that it will be 3.5 meter. Okay, if you take upper half as your free body, then first of all, you are going to put half P. We have P of 40, so that 20 and 20 will be resisted by each column. And if you take moment about J or K, then you are going to find out your N value as such. Okay. After finding the column force, you are going to calculate your base moment, which is 20 times 3.5, which is 70. So this kind of problem can be show up in FE exam or in the final exam, because it's very simple. 20 times half height of the column, that will give you 70 kilonewton meter. So it's pretty much simple enough to be shown in FE exam. After finding out column shear, which is 20K, and the column force 27.5, then you will see that you are going to have 1, 2, 3 unknowns. And I'm going to leave the task of finding these 3 unknowns using 3 force equilibrium equations to you. Okay, as I found, those values are as such. And after finding out those 3 forces, you are going to move to joint D and then joint H using method of joint, and then on the other column. And please note that your column shear is just half of the applied load 40. You memorize it, and so that you can speed up your calculation. Of course, you can use sigma moment about the this or this inflection point to come up with 20, but just memorize it, and the column shears are just half of applied force in total frame. Okay, this is the final result. Using this analysis result, let's try to learn something. When you have 40 kilonewton lateral load due to earthquake, for example, then column shear will be half and another half. And because we are expecting inflection point meter height, which is 3.5 meter from bottom, my moment will be 70, 20 times 3.5. So that you should be able to read this type of total frame as long as you have the lateral force given. Then instantly you should be able to calculate the base shear and base moment. In frames, beams are connected to columns using either rigid connection or pin connection. If the column is very, very stiff as compared to beam, then it may be considered as fixed support. But very rarely column can support beams as a fixed condition. If it's a fixed condition, then bending moment diagram will be like this. And inflection point from the face of the column is 0.21 L if it's totally fixed. But in reality, the rigid connection used in column and beam connection, they are rigid, again, not fixed. Another extreme is pin supported. If your columns are so flexible, then rotational restraint provided by column is very, very limited. So in that case, you may consider it as pin support. In that case, your bending moment diagram shows like this. From the beginning of the beam to the end of the beam, there is no negative bending moment. But in reality, we are in between two extremes, fixed end support and pin-ended. So that our bending moment diagram in reality is somewhat in between A and B. But please pay attention that if you consider the parabola here and also here, the shape and magnitude is exactly the same. But due to moment resistance supported at fixed or rigid connection will pull your bending moment diagram down so that maximum bending moment at midspan will be reduced as fixed condition as support location increase. So if you have very steep column here, then it may be considered as providing fixed end support or near fixed end support to the beam. If your column is so slender, then it's almost free to rotate so that it can be considered as pin. But again, our common reality falls in between these two extremes. So if you look at here, the inflection point is 0.21 L away from column surface. And here pin, it's 0. So 0.21 L plus 0 divided by 2 will be 0.1 L. 0.21 L at a fixed beam, that is exact value. 0 also is exact value. But we do not know in reality your connection is exactly between these two extremes, somewhat in between, so that we need some approximate value, which is 0.1 L. Okay, memorize it. So, approximate location of inflection point at the usually rigidly connected beam is 0.1 L away from support. The key is how to use it. We are going to use in this way. When you look at this type of reality, you are going to model it like this. I found two guys in the class still does not know how to analyze compound beam. I asked you to analyze simple beam first. simple beam portion of the complex beam first, and then use reactions of those simple beam as action to the rest of structure. This one is not complex beam, but the method is exactly the same. We are going to analyze this simple beam whose length is 0.8L because we are going to have cantilever beam, approximate cantilever beam at both sides whose length is 0.1 L each. Okay, so let's solve one example here. It's 20 feet, so 0.1 L will be 2 feet, 0.1 L will be 2 feet, and remaining will be 16 feet. Anyway, this is what you need to have in your mind when you take exam. Okay, analyze simple beam portion first. Like this, because it's uniform load. Again, don't forget you are going to have dashed line here. Textbook does not care about the dashed line, but I explained the importance of the dashed line. Alright, so that half of reaction, half of reaction. And that reaction will be action to the cantilever portion. In that way, you can calculate your moment. Of course, those are approximate values, but good enough, accurate enough for practical purposes. So that your bending moment is like this. Again, let's learn and make sure that this is bending moment diagram for simple beam. And the simple beam bending moment diagram is pulled down by 14.4 in fixed end or rigid end connections because we have negative bending moment occurs at support location. Okay, when you have, for example, two-bay building, we are going to utilize the behavior of portal frame. First, a hinge is assumed at midspan of each girder, like this. And a hinge is assumed at mid-height of each column, as we assumed for portal frame. And the third is the interior column will carry V and interior column will carry double because we are going to model this two-bay frame into two consecutive portal frames so that actually this column and this column is representation of the interior column. So interior column will carry 2V, twice that at the exterior column. So we are going to have V, 2V for interior column, exterior column, V. So we have total 4V. 4V must be same as P. Okay, memorize that formula. Okay, this is what we have.